All right, so good morning, everyone, and welcome to today's lecture. Let me share my screen. Here we are. And let me also minimize this guy. Okay. So this is an example from last day, and you guys supposed to solve it. I'm sure you did. I'm just gonna quickly solve it so you can then compare with my result. We have a book here, and we want to find out the moment of inertia, right? Mass moment of inertia that last day we talked about it, about its axis that passed through its center of gravity. Let's assume that these are the x, y, z. Let's say this is x and y, and then z is gonna come out of that book. So it seems this side is 250 millimeters, and this side is 50, and this side is 200 millimeters. And we have the mass. So it's a box, right? And we have the formula for a box from that table. Simply, we need to write down Ix. Some people write down Ixx, but Ix, when we write Ix, it means Ixx. So Ixx, we look at this axis, right? And the formula is 1/12 m, two numbers squared. In order to avoid confusion, usually what I do, I look at like this axis is normal to this plane, which is 50 by 200. And we need to be careful about the units. So it is 0.2 squared plus squared. And m obviously is 1.5 kilogram. Right? So we'll do the same for Iy, which is 1/12 multiplied by 1.5 kilogram. And it's obvious, right? Y, it's normal to this plane. And so simply it's going to be squared plus 0.5 squared. And whenever you forget the formula, always the tables are available, either in your exam and in future when you are calculating this for something. The tables are online. If you just Google mass moment of inertia for a cube or for a box, rectangular box, then it is there. You don't need to memorize them. It's not a bad things to have some of the common one memorized, like a slender bar or a box, a disc, but in general, you don't need to. Iz, so it's gonna be 1/12 and 0.2 squared plus 2.5 squared. All right, so I believe most of you solved this correctly. And but if you have any question, please feel free to ask. And don't forget about the unit. So the unit we talk about, it's going to be kilogram meter squared. So the same question, if we want to find out the radius of gyration, how would you calculate that? So radius of gyration, we show it by k, and k simply is square root of I over m, right? So you can calculate Ix then. Simply it is Ix over m. And the unit is going to be meter. Right? And so on. You can calculate Ky and Kz. So if you want to take notes, please do. And if you have questions, please ask. Otherwise, let's go to the next example. I'm going to wait here for 10 seconds to see if you guys have any question. Okay, I assume you guys are good. Then let's solve for this one. So this simply asks to find the mass moment of inertia about its center, and it is a slender bar, right? So if I set, let's say, my axis to be at its center of mass, let's say to be like this one. And it doesn't matter which one we select as X, which one as Y, and which one as Z. So because it's a slender bar and the question, ignore the radius, like the diameter or smalls. So it is almost equal to 0. Then it means we ignore Ix and we say almost it is 0. Because it's symmetric, Iy and Iz, they are the same, right? So this is then the center of gravity, G. Iy is equal to Iz. And for a slender bar, we have the formula 1/12 L squared. We have M and we have L, right? So it's going to be 1/12, 2 kilogram, and L is 2 meter. So simplify this one, it's going to be 2/3 kilogram meter squared. So if this question asks us to find, let's say, I about this axis, like at one end, and it doesn't matter which end, mass moment of inertia is always positive. So how can we find I about this axis? So of course we have the table, but let's say we just know the formula or the value for center of gravity. We talk about this, we use the transfer axis theorem, right? The parallel axis theorem. So I about this axis is equal to I bar plus mass and the distance, which in this case is L/2 squared, right? Which if we simplify this one, we will get the same formula, 1/12 mL squared plus m squared gives us this one, which we have it in our formula, in our table. So 1/3 m is 2 kilogram and L is 2 meter squared. And obviously I for these two axes are the same, right? Because of symmetry. It doesn't matter if you look at this link normal, like in Y direction or in Z direction, we'll see the same things. I'm gonna wait here to see if you guys have any question. If not, I'll go to the next example. I'm just gonna go fast because these are super easy. I believe. And the same, you can find radius of gyration for each of these. The formula is simple. Radius of gyration is I over K. So let's solve this example and see what it asks. So it says that you have a coin one time flat on your table, one time in a vertical position. And we want to figure out which way it's require less less torque to spin it. Most likely you can guess, but we want to see it mathematically. And assuming there is no friction, like the one flat, assume that between the coin and your table, there is oil, so it can spin easily. And this one the same. What would be your guess? Which one requires less M, assuming that we want them to spin at the same speed? Or as the question says, we want them to get to a certain speed it means we want them to have same alpha, right? Because omega is always equal to alpha t. So let's say I want to apply a torque. So these two start spinning, and in 1 second, I want them to get to the same speed. So you can type it in the chat and tell me, what is your guess? Which one require less M? Or we can ask this question. If we apply the same M, which one is going to start spinning faster? The one on the right or the one on the left? Or the flat one or the vertical one? So let's look at your guess. So the vertical one, any other guess? And then the left one from Eric, Felix, vertical. So it seems you're all in favor of the vertical one. Sorry. And your guess is correct, but let's see mathematically if it is right. So early in this lecture, which was last day, we said, when we define moment of inertia, we said moment of inertia is resistance to rotation, right? So similar to the Newton law, F equal to, we said something A, we had the same formula for M. M is equal to something alpha. So which this something was what we call it mass, resistance to acceleration, and this one we call it moment of inertia. So in the same manner, if we have a larger mass, it means it requires more force to move it. If we have a mass that has a larger moment of inertia, it requires bigger M. In this case, these two have the same mass, but because of the difference in geometry, one is flat, one is vertical, maybe they have a different moment of inertia, and we want to calculate that. Again, we will look up the table and we will see I for this guy, okay? If I move back on my table, this is following a cylinder, right? The solid cylinder, not that one. Moving back to our table. Okay, where is the cylinder? Here is the cylinder. And here are the formula. Normal to this circle is 1/2 mr squared. And for two other axes, it is 1/4 mr squared plus something more like a slender bar, 1/12 ml2. So let's go back and write them up here. So this one then is going to be 1/4 mr squared. It shows by capital R, right? Here it says capital R. Plus 1/12 m t squared. The formula was L, but here it's T. Show it by T. And this one is 1/2 mr squared. So obviously this is 1/2, T is very small. If you plugged in the numbers, obviously it seems this is way too larger. I'll let you to do the calculation later, but it's obvious, right? We have 1/4 here, here we have 1/2. And 1/12 mt squared is very small. So this is larger. If this one is larger, it means the one on the left moves faster. Faster speed. Or it asks for which one requires less torque. So less torque. Easy, right? So simple concept. And it's important to understand these things. And please let me know if any part is not clear to you guys. Okay, if we are good for that part, and now let's solve one example, which maybe it's worth 10 kilograms of gold. What would you do if you guys had 10 kilograms of gold? Would you continue studying or no? I'm sure you would. So here is the question. Let's say I have a disk and like this 10 kilograms of gold. So we have the mass and let's say we have the radius. If we don't, because we have probably the density of the gold, so we can find the radius, assuming that we know the thickness. So what is I about this axis? So again, similar to the previous example, it is 1/2 m r squared. Now I want to find out I about this axis. Okay, parallel to the other one. So you have about 30 seconds. And then I'm going to ask somebody to tell me what is I about this axis. So assume the radius is R, right? Radius is R, and let's say the thickness is T. So here is the question then, right? We want to know what is I. Just a general formula. You don't need to substitute any values. Okay, so you must be done. So let me randomly ask for Alex. Alex, could you tell us what's the value you got? Or you may just type it in the chat if your microphone doesn't work. Alex, you're not there? What about Rohit? Oh, Alex, you type it. Sorry. Okay, I didn't check the chat. So 3/2 mr squared. That's correct. Yep. So I for this one will be 3/2 mr squared. And that's because of the parallel axis theorem, right? Okay, good. So this is all about mass moment of inertia. And I hope you guys understand this topic well, because this is the base for the rest of calculation in this chapter. Moving to lecture 2 or part 2 of this lecture. Okay, so here are the sections that you need to study, and please study these sections. These are important sample problems, and I emphasize this chapter is not an easy chapter. I try to simplify it as much as possible, and the way that I explain it should not mislead you that, oh, okay, this is easy. I wish somebody taught me dynamics this way. So because this chapter is challenging this topic. And I emphasize, I try to solve simple example, basic examples, so you could grasp the concept. But then it depends on you to solve as many possible examples so you could master this topic. All right. Unlike the previous chapter, it requires a little bit of attention and you need to practice some good problems. So your textbook, the sample problems, please study them. And also, I haven't, but I have the problem set 6 ready. I will post them right after the lecture on Canvas. And some of the problems I provided video solution. So watch them during this weekend. When I post these, I will set you guys an announcement, probably today. Okay, so let's see what this chapter is about. It's about Euler's law. Euler's, a scientist like Newton gives us the equation for a particle, right? And then Euler's came and said, oh, what about a rigid body? And he developed the formula for a rigid body. So what he said basically is, if you have a rigid body like the one on the left, and you, assuming that you know how to draw a free body diagram, you draw your free body diagram, force 1, force 2, maybe even there is an M, whatever you have here, okay? And let's assume that this mass or rigid body has a center of gravity. We show it by G. And because of these forces, this rigid body can move and maybe rotate. So whenever a rigid body moves, we have an acceleration, or it may go with a constant speed. So a bar be 0, and it may rotate. So if it rotates, it might have an alpha, or might be rotating with a constant speed. So alpha is 0. But this is a general case. We draw another diagram here, which we call it a kinetic diagram, or some people call it acceleration diagram, right? And this diagram says, okay, if I have an acceleration a bar and angular acceleration alpha, then it means something is pushing these things with a force of ma bar and rotating this with a moment or torque of I bar alpha. And these two are equal. So the Euler's law, the first and second law, are as simple as this, that sum of the forces, like similar to the Newton law, sum of the forces are equal to ma bar. No difference between this law and the Newton's second law. But for Euler, this is the first law. What is the second law? The second law says sum of the torque are equal to, so here, wait, when we say sum of the torque, always, when we talk about torque, we should immediately say about which point? Here, about gravity. So sum of the moment about gravity, right? Moment of these forces, right? Which you know how to calculate. For example, for F1, it is F1 multiplied by the distance. So which the distance, you need to calculate the distance, the normal distance, right? Like L, this distance here. And for F2, this is your L, and so on, right? L1. So let's do it correctly. So if this is F2, one, if I draw a parallel line to that, then this is the distance which I can calculate m, right? So this is L1. And similarly, if let's say I continue the line here, maybe with a different color. So this will be my L2. So you learn it in static in 260. So you should be good with that. And same for F3. So we calculate m about point G, but for us here, this other side of equation is important. It is equal to I alpha. Which I? I bar. All right. And this is the second law of Euler. So that's his first law. And this is his second law. Okay. Seems simple. That's all. And the rest of this lecture is just using these two equations to solve problems. Also, he did one other good things for us, like this guy, Euler. He said, what if one day you need to take moment about another point, another random point. Let's call point P. What should we do now? So he proved, so point P, that That's okay. You just take the moment about point P. But you need to be careful. The moment about point P, the first part stay the same. So I bar alpha. There is another extra term here. And that extra term is M A bar. Like you see, M A bar. Then somehow you need to think about this M A bar as a force. So this force creates a moment about point P, multiplied by the distance, normal distance between this point and MA bar. So let's call this distance D. All right. So this is D. And this is D. So this is also Euler's second law, but that's a new version of this sum of the moment about G is equal to that. And another bad mistake that I saw it a lot is that the student write sum of the moment about P is equal to IP alpha. And this is a very bad mistake. Euler would be very upset in his grave. Okay, so any question, guys, here? Let's then apply this equation to a very specific case, a case that a rigid body rotates about a fixed point. Okay, so the previous one was a general case, a rigid body rotating and moving. This one is being fixed on a point, a special case. So we know if something is spinning about a point, then let's say its center of gravity is G, it has two components of acceleration. One is AT and one is AN. And R bar, it means this distance here. Like the distance between point O and G. This is what it means by R bar. Okay, so if you guys agree for these two components of acceleration, AT and AN, R alpha and R omega squared, then let's write down the equation of motion for this guy. So let's write down the second law, sum of the moment about point O are equal to, what should I write? So let's move back to our formula. It says sum of the moment about any point other than G is equal to this formula. So okay, let me write it down. It's then I emphasize I bar, okay, plus I bar alpha plus M A bar, and then D, which D here for us, let's write down the formula one time. So let's keep this first part as it is. And here, I just want your attention for 10 seconds. MA bar, right? I look at the acceleration at point G. So it has two acceleration. I should write down both here. Like here, it should be a bar. Let's write it down one more time. M a bar t multiplied by distance. What is this distance? It's r bar plus m a bar n. What is the distance for a bar n? You can type it in a chat for me. So this is our general formula from our friends Euler, right? But a bar here now, we have two components. We have AT and AN. We need to write it down once for AT, one for AN. So the distance for AT is obvious. It is R bar. What about AN? Let me see what you got in the chat. 0. That's correct. Thank you, guys. You guys are good. So it means it makes my life easier. Because whenever something is passing through a point, its distance is 0, right? Simple as that. So let's simplify that one more step. What is AT, A bar T? It is R bar alpha multiplied by R bar. Then I can write down I bar plus M R bar squared alpha. So is this something familiar to you guys? I bar plus M R bar squared. Does it mean anything to you? What it says? I bar, think about an axis at G coming out of a screen, plus mass multiplied by R bar squared, which R bar is the distance between G and O. What does it mean? Is it equivalent to something or no? Any idea? You can type in the chat. So the question is I bar plus M R bar squared, is it equal to something or no? Just to give you a hint, think about the parallel axis theorem. I'm gonna check chat to see if you guys. It is IO. And also I missed one question here from Felix. Why we didn't write AN? We could write AN T squared plus A bar N squared, right? But we would make our life more difficult. So Felix is asking, like, rather than like this equation MA bar D, rather than break it down to A bar T and A bar N, should we find the equivalent of A bar N and A bar T, which is like this one, right? I'm just gonna do it one more time because that's a good question. So a total bar, which is AT squared plus AN squared, right? All of them bar. And also we need to find its direction. And then we need to find the distance between this point O and this guy, like this distance, let's call it D. It is also correct. However, it's a headache to find this distance D. So always when you can use the components of a force or an acceleration, stick with the components. It makes it easier for you. Both are equivalent, okay? So for all of you guys, because it was a good and important question that Felix asked, let's pay attention one more time. So he asked, like this Euler formula that I have, MA bar, A bar here means the total acceleration. So if we wanted to do it correctly, we should have calculated the total A bar, right? Which is like A bar T squared plus A bar N squared and the square root of them. And then we should have calculated the distance from that vector to point O. But since it's not an easy task, always when you are working with a total of something and the components are there, why not break it to its component and work with the components? Okay, so let me clean up all of that and continue on our solution. And somebody was right, I forgot who said, Cameron, yes, that's correct, Cameron. This is IO. Okay, let's then write the formula one more time. Sum of the moment about point O is equal to IO alpha. Okay, here I want your attention, please, for 10 seconds. So you may say, wait a moment, let's move one slide back. You said this is a very bad mistake. Sum of the moment about point P, any point other than gravity, the center of gravity. Any point other than center of gravity. You may say, well, you said this is a very bad mistake and we should use the Euler formula. But here we just said something different. We said sum of the moment about point O is IO alpha. And O is not center of gravity. And here is something that you should remember. We only allow to use this formula if O is a fixed point, is a joint, like here, okay? Not for any other point. A fixed joint. Or I'd better write a fixed to the ground joint. Okay. And that's why sometimes the students make mistake. They look at this formula and then if they are writing equation for any other point, P, just like, oh, okay, it is IP alpha, and this is a bad mistake. And now we want to solve example using these 4 equations, 1, 2, 3, and 4, which 4 is for a special case. And here is an example which we want to solve it together, at least the first part. And then you guys can continue the rest. I'll let you guys to read this. And think about how we can solve it. Always start with the free body diagram. And remember here in dynamics, we have 2 free body diagrams. One is, or I should say we have 2 diagrams. One is free body diagrams for the forces. One is the kinetic diagrams, the acceleration diagram, right? So you have 30 seconds to think about it, and then I will ask somebody to tell us what he got. And while you're thinking about it, I will draw. Okay. So we want to then draw the force diagram and the acceleration diagram. Okay. So I'm gonna draw the force diagram here. So we have here a x and a y. And you guys know we have the mass, right? mg. And mg is our center of gravity. So what about the acceleration diagram? We know that this thing can rotate about a fixed point, right? And that fixed point is A. So we should know whenever something is rotating, like a bar, this one, it has two components of acceleration. One is AT and one is AN. So this is AT, A bar T, and this is A bar. Let's write it as a like this. Sorry, this is N, and this is T. Okay? And also we know these things has an alpha. So our force diagram and our kinetic diagram. So guys, let's, if you guys can wait here for 5 minutes, let's get at least the first part of this question done. Okay, so sorry for keeping you here. And I guess you guys need to also attend your tutorial, which is an important tutorial about CAM mechanism. So I suggest attend please that session, although you guys have a midterm, but anyway. So we have the diagram. Did we miss anything, or you guys think that's okay? So if, again, I emphasize it, if you can draw a good free body diagram and a good acceleration diagram, it's almost you solve the problem. Because the rest, you know, so like A bar T here is equal to L over 2 alpha, and A bar N here is equal to R omega squared, right? Which R here for us is L over 2 omega squared. And what else? That's all. So what we need to do, writing the Euler's equation. Let's start writing them here. So I will write here, but first, should I, okay, use the, something maybe we can think about it. Should we use the coordinate like horizontally, or you think we're better off using X, Y along this guy and normal to this. I suggest this one is better, right? Because it's easier to work with the direction that AT and AN they are. So in that case, let's then change this guy, AT and AN. So the previous solution was correct, but more work. So, and I assume positive direction. If you are wrong, you're going to get negative numbers, but that's okay. So this is AY and this is AX. Now our work is less because we just need to find the component of this mg. Let's for today write the first equation of Euler, the second one. Sum of the moment about point A is equal to IA alpha. And you need to tell me if it is wrong. Sum of the moment about point A is AA alpha. Is it correct or no? Should be right, because A is a point that this link is fixed to the ground. It means I'm allowed to use this formula. So let's quickly write it down. What is the moment of these loads about point A? I have only mg. I can find its components. Let's quickly do that. One component in X and one in Y direction. So it's going to be mg here and mg there. All right. So if that angle is theta, this angle has to be theta. So this is mg sine theta. And correct me if I'm wrong. So mg, right, cosine theta multiplied by its distance, which is L over 2. And we can assume one direction to be positive. Let's assume it's up to us. If we are rotating in this direction and we consider it positive, let's stick with that to be positive. But you need to be consistent. Or you can consider this negative, that doesn't matter. So this is the moment about point A. It's equal to IA, which for a link IA is 1 over 3 ml squared alpha, right? Remember, for a link or for a bar, I about one end is 1 over 3 ml squared. One end, like whatever that point is. So if I simplify that, I would get alpha is equal to 3 over 2 GL cosine theta. So this is alpha. Our next step is finding omega, and that's something that you're going to think about, because Monday, the first things that I'm going to ask is somebody tell me what is omega. Okay, so we found alpha, and it is a function of theta. It's not constant, and we need to find omega. What is omega? And you know the formula, right? Whenever you have alpha and you want to find out omega as a function of theta, the position, what should you do? That's enough for today. Thanks for waiting. I'll see you guys on Monday. All right. Let me stop sharing here. And I can stay in the room if you guys have any question. If not, then good luck with the tutorial, which is start in few minutes. Bye for now.